process hierarchy and process states. So last time we learned state diagrams, 2-state diagram and 5-state model, right? 2 models. So we'll talk more about those things. So again, you have to remind process. What is process? Process is a program in execution, right? So in operating systems, there can be many processes run executing programs. They are not referring to hardware processor, the CPU, but software programs. Right. In the introduction, now you have a good knowledge on process creation termination method. So we have learned how to create a process, how to terminate process. And also in the previous lesson, we discussed about 2 process models. Therefore, in this lesson, you will be able to learn about different process states and the hierarchical structure processes can have. So after the completion of this lesson, we will be able to illustrate process hierarchy. So what is? Furthermore, you will also be able to explain different states of a process. Last time also we talked about different states: running state, lock state, and so on. So lock state, entering, exit, right? So again, when we talk about them again, you will understand. So here we are talking about process hierarchy. We should be able to describe. Then list different process states. Also explain different process status with some examples. Okay. So let's go on. So what is process hierarchy? If a process creates another process. Now we have heard about child processes. One process can activate another process. So if a process creates another process, then we have parent and child, right? The parent process and the child process. Where you can see the person now. The parent process and child process continue to be associated in a certain way. So there's a kind of relationship. The child process also can create one or more child processes. So any process can create many other processes. So child process also can create one or more child processes. Then it will become like tree. That's the hierarchy. The important fact is that each child process can have only one parent. The parent can have many children, but child can have only one parent. So there's something to remember. Now all the child and parent process group together and form a process group in Unix system. So Unix operating system, there's something called process group. It's the collection of all child and parent processes. Therefore, when a user sends a signal from the keyboard, for example, if you type character A, the signal will be delivered to all the members of the process group currently associated with keyboard. So we can group the processors currently associated with keyboard. For example, expecting inputs from keyboard, there can be many processors. So it is one such group, right? So when you press a key, all such processors received that in that group. Then each process can catch the signal individually, ignore the signal or take necessary action to the signal. So all are associated with keyboard, the processors are grouped together. So your key entering signal sent to all the processors in that group. So certain the processors, if they are expecting signal, they can process it. If you are not expecting that, you can just ignore the signal. Okay, so that's how in Unix operating system they work. Now, even though Unix systems have the concept of process hierarchy, even though they have hierarchy, Windows systems do not have this concept. Now, even now the one group of processors associated in keyboard, another group may be accessing system files, root directory, and so on. There's a kind of hierarchy in Unix system. But when you come to Windows system do not have this concept. In a Windows system, all the processors are equal. So Windows, all the processors are equal. The only place where process hierarchy concept is applied is the process creation, right? Where the parent receives a special token to control the child. So Windows, when you create, parent receives special token. So parent can identify the child and control accordingly. But this token can be passed to any process. For example, sometimes we kill processors. If you want to kill a parent process, you have to pass this token to another, right? So passing means you invalidate the hierarchy. But process in Unix cannot disinherit their children. So that's the difference between Windows and Unix implementation. So Windows, you can pass the parent state to another. How? You pass the token. But Unix, you can't do that. So passing token means then it will have another hierarchy. Okay. So, do you have any questions? If you have any other questions, if you don't understand anything, please ask. Then only I explain again. Otherwise, I assume you understood and continue. Okay. But, that's about hierarchy. So you should remember now. Unix, you have a kind of fixed hierarchy. But Windows, time to time, the initial hierarchy may change during execution. Yes, you can change the parent state, pass parent state from one process to another, but only in Windows, not in Unix. Okay. So next one, process states. We have talked about process states earlier also. Yes, still more waiting. Let me edit. Even though each process is an independent entity, and you know, when you call the process, it can run independently. The process may generate an output. Even they work independently, one process may generate output. It can be used by another process. That means there's a kind of dependency also. So if you take one process, if it is independent from another, they can run independently, but one may wait for results from another process. For example, consider this. Process A, capital A, will calculate the values of x plus y. Okay, so process A is to calculate the result of x plus y. After calculating it, store it in a variable called z. Similarly, process B will calculate the value of z and w. Now what will happen? Process B required value of z, but this value is calculated from the process A. Process A has to calculate the z value is the x plus y. Right? So now you can see the process B used the result of process A. Therefore, output of process A will be used by process B. So even process A and B are independent processors, there's a kind of dependency because B has to wait until it calculate Z value. Okay. Now what will happen? The process can be blocked. Now process B can be blocked until it gets the Z value. Right? Even they are independent, now process A can, if process A is not calculating this, process B is being blocked. Right? Due to two reasons. Firstly, a process may be blocked because it is waiting for input. Now process B is waiting for the Z as input, which is not yet available. So it has to wait until process A calculates it. That is not complete. So that is one type of waiting on block state. Secondly, even when a process is conceptually ready, let's say now we got the value of z, so conceptually it is ready to execute. But how about if the CPU is not available, used by another process? Something like operating system may decide to allocate the CPU to another process. Again, until it gets the time, it is being blocked. So these are the two types of blocking situations. So if you are waiting for an input, you are blocked. If all inputs are ready, but CPU, the resource is not available, again, you are in the blocked state. Now, according to these situations, process can have three states. What are the three states? Running state, ready state, and the blocked. So that's why we get this, the second model. Okay. Now, since we have explained these two situations, the process can be running state or it can be in the block state. But we can add one more additional one. That means it is not really blocked because if you get inputs, it is in the ready state, but waiting for the run. Right? So this diagram is a very simple diagram. You understand, right? So what are the process states in this diagram? Running state, ready state, and the block state. So what are those arrows? They are known as transition. transition. So this arrow indicates transition from running state to block state. How to transit. This arrow explains transition from running state to ready state. This arrow you can see it is from block state to ready state transition. This arrow ready state to running state. Now we should be able to explain each of these transitions. For example, if you are asked to explain the transition 1, that is from running state to block 1. How can it happen? For example, if there's a running process and now you know CPU is time sharing. So let's say process A is running. But if your time slot, allocated time slot is finished, you can't run any longer because you have to give chance to another process. So what will happen? You transit process A from running state to block state. Or if it is waiting for another results, you can transit to block state. If it can still execute, but you are stopping running state because you have to give the resource or CPU power to another process. Then it is ready to run, but you have to wait for a while. Therefore, you can put from here to here. So when you are in the ready state, if CPU time is available again, you can move it to running state. Okay, ready to running state. If you are in a block state for an event, maybe a result from another process, once you get that, you can move that to block state to ready state. Okay, so I hope it is clear. Transitions. So you have 3 states: running, ready, and block. Running means actively using the CPU at that instance. So it is using CPU and executing running. Ready means it is not in the running state, but it is runnable, but temporary stop. Okay. Block means even CPU power is available, you cannot run because inputs are not ready. It's unable to run until an external event occurs. Okay. So between these 3 states, running, ready, and blocked of the process, how many transitions you can define? 4 types of transition methods can occur. Like in this diagram. So how many transitions? 1, 2, 3, and 4. So you have 4 transitions. So what is the first one? First one, process blocks for input. So you move it. If you need the input while you are running, you move it to block state so that you can give this processing chance to another ready process. Okay. So first one is process blocks for input. So if you are waiting for an input, you can put that to block state. Then the second is it says scheduler picks another process. So in operating systems, you have separate section or module called scheduler. Is the one deciding which one to move from here to there and so on. So scheduler, if you move one from running state to block 1, scheduler knows now CPU power is available. So scheduler pick another process to run. So that is another transition. So scheduler picks another process, scheduler picks this process, input becomes available. This in so if scheduler pick one, this is the transition. Third. Okay. If input becomes available, then scheduler will change it from block to ready. You can move it from block to ready. Okay. So again, this diagram is from Operating System Internals and Design Principles by William Stellings, one of the reference books I have mentioned to you last time. So I hope up to now it is clear. So let's go. So transition 1 occurs when it is run. Transition 1 occurs when a process is running, right? This is the transition 1. Transition 1 moves process from running state to block stage. So 1 occurs when it is running. If the running process is waiting for an IO operation, input output, for example, maybe it is waiting for your username and password, right? So IO operation. Then it will be blocked until you read the like keyboard input. You have to wait, right? So if user is slow, you have to wait until you get it. So that means it is being blocked. So it is the transition 1. So like this, you should be able to explain it, okay, using your own words, right? So this is what transition 1 is. Similarly, you can explain transition 2. Transition 2 and 3 is the 3 are caused by the process scheduler. So scheduler picked one from ready state to running state. Or scheduler may say, okay, your time out. So move back to ready state and give chance to another one. Like that. Okay. If the scheduler decides a process to be run within the CPU, maybe high priority process comes, the scheduler gives that chance to it. Okay. Then second transition will occur, right? If it decides to give another chance to one from ready, this third scheduler decides process to be run within the CPU, then the second transition will occur. Second means whatever exists in one, you have to put back to ready. Transition 3 occurs when all the processes had their fair share. And it is the time for the first process to run it again. That is if you consider the same process. Let's say now process A is running here. So scheduler knows when to stop when the time slot allocated finish. So scheduler put that into ready state. In a normal conditions, scheduler give chance to all other waiting processes. Once all get chances, again scheduler decide to take the initial one, that is process A again. right? So that is transition 3. That's why this explanation. So transition 3 occurs when all the processes had their fair share, and it is the time for the first process to run it again, right? So it is important to decide which process should run and also for how long. Okay, so there should be someone, what we call scheduler, right, to decide, okay, next which process should run and how long you allocate for that. So how to do that? It's another difficult one, and we'll discuss in says lesson 9. Right? So you have to learn how to schedule also. Scheduler, because there's no one inside the computer to decide. You have to program. The scheduler also another program you have to think and write. Okay? So we have to learn that also when designing operating systems. Then the fourth transition occurs when an external event for which the process is waiting is occurred. So fourth one is, you remember that from blocking state to ready state. So if an event occurs, it is waiting for example, keyboard input came, then you can move to ready state. Okay. If the user entered the, for example, his username and password, now next step is you have to check it whether it is correct. So checking part you need CPU power matching. So you can move back to ready state until you get the chance of processing. Right? So this very simple thing. So this last lesson we discussed different process models, 2-state model and 5-state model, right? Therefore, by using the process models and process states, it's easier to visualize what is going on inside the system. So if you diagrammatically represent, then for us humans, easy to visualize what is happening. Okay. But inside the computer program, you don't have these nice diagrams. It is only a program. But to illustrate this concept, we use such diagrams because for us it's easy to visualize and understand. So as the course moves, you will be able to learn how the processes are selected to CPU, how to interact with other processes, and other related issues in an operating system in detail. Okay, so this I think short lesson. So now you should be able to explain each process transition method in your own words. Right? You don't have to memorize this, but when you understand the concept, you can explain it using your own words. So that's it for this. Now we have completed lesson 5. In this lesson, we have discussed process hierarchical structure and different process states within a system. Right? Next lesson, you will learn the concept behind threads models. You may have asked heard the multi-threading and operating systems and so on. So you need to learn about this. So earlier operating systems, they use this process concepts, process hierarchy, right? We learn what is the process and what is the thread. So threads, you have user level threads, kernel level threads. Before you go to the next lesson, complete this process. Right. So do you need a break or can we continue with the next lesson? Right, now you can see the lecture 6. So here we are going to talk about thread models and usage. Previous lesson we have discussed different process status and the hierarchy of the processes. Therefore, in this lesson, different thread models and thread usage will be explained. In addition, you will be able to differentiate between user space threads and kernel space threads. So we learn what they are. And at the end of this lesson, you will get an idea of difference between processors and thread. So you should be able to explain. Now you know what process is. And after this lesson, we learn thread. And you should be able to compare the difference between threads and processors. After completion of this lesson, you will be able to explain different thread models with thread usage. In addition, you will be able to differentiate user space threads and kernel space threads. Therefore, the lesson would enable you to describe different thread models, explain the usage of threads, then list advantages and disadvantages between those two user space threads and kernel space threads. Also describe the features of user space threads and kernel space threads. So, what is thread model? Now you know the process is a unit of resource allocation and the unit of protection. Process also has a thread of execution. Now process can have a execution thread. That means process can have more than one. A single process could consist a number of threads. Okay, so that is one of the differences. Process could consist of number of threads. Then you will get an idea. So process can be broken into threads. Threads are entities scheduled for execution on the CPU. Okay, so this is the definition. What is thread? Threads are entities scheduled for execution on the CPU, not whole process. Process is the whole programming execution, but inside that there can be various parts. So threads schedule CPU, right, to execute. Therefore, invariably, a thread must execute within a process, right? So thread is the execution part of the process on CPU. Therefore, thread must execute within a process. Now, similar to a process, the thread has, so what's the similarity? Something called program counter. Why we use program count? Used to indicate the instruction that needs to be executed next. So when you are running a program, you have number of instructions in your program. But we keep something called program count. So when you execute one instruction, this program counter will show us what to execute next. Okay. So in the program counter, it's in the order of instructions you may run during execution. Now, when you write a program, sometimes if you write C++ or Java, sometimes you don't execute it in the same order line by line. Sometimes you may have loops, or you may direct it to different sections like procedures and so on, right? It is not the order you are executing when you execute the program. Time you have different pointers to move here and there. But program counter, it has the exact order of executing instruction by instruction. Okay, so you should learn these terms. Then what are registers? Registers also kind of memory, short-term memory. For example, now inside the CPU to do certain operation, for example, now A plus B, to calculate that you need to load value of A to the CPU and value of C to the CPU. So where do you keep them? Those locations are known as registers. So compared to main memory of hard disk, these are very limited storage. So give me a second. Hello. Hello. Oh, Sirvan. Oh, මම මේ දැනුත් ලෙක්චර් එකක ඉන්නේ මම ගත්තේ අර මේ ටේබල් එක තාම අතන තියෙනවා එහෙනම්. ඕකේ අර ඒ කවුද මිස් කෙනෙක් ඉන්නේ ડોක්ටර් වරාම ඒක තියෙන්නේ අර පරණ රූම් එකේ. ඔව්. හරි. ඒක චුට්ටක් බලන්න මොකද දැන් අර ඒකේ තියෙනවා. right? Okay. Okay, sorry about that. Now, continue again. So, registers are the small storage locations. For example, within a chip or CPU, temporarily you have to store certain values. For that, we use registers. So, when compared to main memory or hard disk, registers are very small because inside the CPU you can't have that much space now. That's why time to time you have to load values from memory to register the CPU. Then pass the result back to memory. Then load another one for next calculation. And so on. Right? All right, number. So compared to memory or hard disk, registers are very fast because it's within the CPU, right? Hardwired, so you can execute very quickly. But unfortunately, you can't store lot in registers because the space available is very limited. Then there's another one called stack. So when you're running a program, we store the history. So time to time, we may have to recover. Or for example, when you are running a program, actually you can't use CPU continuously because you have to share it with other processors. So time to time, when you put that process into block state or ready state from the running, you have to keep the track how much you have executed. So that you need the history. If you need to recover and also run from where you stopped, this history also very important. So where do you store them? Some place called stack. Okay. So as computer student, you should know these terms. Maybe in other subjects, you may learn this. Okay. Now, threads have some of the properties. Now we are talking about threads, right? Threads have some of the properties of processors. Therefore, they are called as lightweight processors. Because within the process, there can be many threads. So therefore, sometimes they are called lightweight processors. Okay. So that is another term. Threads enable multiple executions in the same process. So that's another advantage. Maybe same program, different sections you can run parallel. So this can be done using the thread concept. So threads enable multiple executions in the same process environment independent of each other. Okay. For example, your program maybe one section you may have to read values from hard disk or database. So you can run it independently from another section doing another task. But normal programs you can't run two sections of the same program at the same time, but using this thread concept, you can do that. Okay. So multiple threads running in parallel within a single process is known as multi-threading. So that is what we call multi-threading. So latest operating systems, Windows 10 and so on, they are multi-thread operating systems. That means same process, different parts can execute parallel, right? Because you can run different threads. So one process can have many threads, right? So this scenario is similar to having multiple processors running parallel within the same computer. Right? Now we are running different processors in a computer, different applications at the same time. So similar concept you can apply within a process also. So that is called multi-threading. So if you do not have this concept, then it is called single thread. Right? So before the multi-thread concepts, we had only single thread approach. A single thread of execution is carried out within a process. Right? But now this multi-thread concept make it more complex for the operating system design. That's why the first multi-thread concept came in, I think, Windows 95, and it was not stable. There were so many problems, bugs, because the operating system designers, it's very difficult to handle, right? That's why it got stuck time to time, and you have to reboot. Okay. So different types of operating systems have single or the multi-threading capacity. So now you know a few different operating systems. If in the MS-DOS, that is the earlier version, it is a single process. You can run only single process at a given time, and single thread system. That's the very old operating system, MS-DOS. So it is running single process, single thread system. Right? Then Unix operating system. It allows multiple processors, not single process. So MS-DOS you can run only one program at a time, one process at a time. But Unix you can run multiple processes. But still it has single thread concept. Okay. So I have increased the font size so you can hope you can read easily. Then we have something called, I think you are familiar, Java runtime environment. So in that case, it allows you are running only one process, but you can run multiple threads of it. So that is what this Java runtime environment supports. Okay, same program, you can run many different threads. Same process, you can run many different threads in Java runtime environment. Then if you consider other latest versions of Windows, another operating system called Solaris, and Mac operating system like Apple computers. Then OS2 you'll find IBM mainframes and so on, the large computers. They allow multiple processors with multiple threads. Okay, they allow multiple processors with multiple threads. Okay. Now you should know multi-processing and multi-threading. So earlier we had multi-processing system. Like you can run many different processors at the same time. So many operating systems. You can run like Unix, multiple processors. It is multiple. And all those you can run multiple processors. But when you come to thread concept, within a process you have many threads, so you can run them parallel, multi-thread. Right. The CPU switches back and forth among the different threads. So when you are running multi-thread, inside the CPU you can run only one thread at a time if you have one CPU, right? So one thread at a time. Then CPU switching between back and forth among the different threads, right? So I think you can imagine this kind of situation. So, unlike different processes, different threads in a process are not completely independent of each other. So when you consider process to process, so different processes, not like that. In different threads in one process are not completely independent of each other. If we consider two processes like two applications, they are independent. But one application might use output of another. It's a different story, but they can run independently. They are totally independent. They share different data sets, different memory locations, and so on. But if you consider threads in one process, they are not completely independent because they are in the same program, right? So different threads in that process are not completely independent of each other. Why? They have to share the same memory. So same address space, same the access to same data and files and other resources. Because threads are leading the process, so whatever process the threads can access. So threads share the same address space, same memory, and so on, right? Like same files and other resources. You get the concept? If these are not clear, you can ask. So every thread of a process, right, can access all the memory addresses within that process, right? But not the memory address in other processes, right? So thread can access the memory addresses within the process, all the address space allocated for that process. And also something called global variables of the process are available to all the threads. So all threads can share global variables. Therefore, there is no protection. Why? One thread can update variable used by another thread. So how can be there's protection? So therefore, there is no protection. So programmer, you have to take care about this. Therefore, there is no protection among threads belonging to a single process. Okay. So in a way, that's a disadvantage. Less protection. But unlike different processors, smaller thing, maybe you can treat. Right. Unlike different processors, which might be hostile to each other, the threads within a process can coexist with each other. Coexist. Right? In parallel, they can exist. At the same time, they can exist, right? Run. Therefore, protection mechanisms for threads within a process are not required. So you don't have to worry that much about protection mechanisms. Right? This design can protect them. While some of the resources within a process are shared by different threads, some other items must be kept exclusively with each other. So let's see comparison. The process what you have, the thread item what you have. Check whether you can understand each term. If you don't know, you can ask. The process items you have address space. So within the memory, remember we allocate certain space for process when during the process creation, right? So when you create a process, you have to allocate all these address space, global variables for it, the open files, then the process can create child processes, pending alarms, signals and signal handlers, also counting information. So process should have so many things, but if you consider one thread item, of course it has a program counter which instruction to run next, then registers for local variables, temporary store certain data, then stack. What is stack? You keep the history of execution, thread state, so whether it is running state, block state, and like that. Okay, but not other controlling things you don't need because they are being handled by the process. Okay. So similar to process, okay. Similar to a process, the thread has different states, right? What are the states? Now you have learned running state, block state, ready or terminated state. So these are the states of a thread. Running means same meaning. A running thread is active and currently holds the CPU. So which one is running on the CPU? Block means it is not in the CPU, no? If it is blocked. A block thread is waiting for an event to unblock it. Unblocking can be done due to an external event flow by another thread. External event is like waiting for a keyboard input. Another thread also can activate. Then ready and terminated. Ready to schedule to run and will execute as soon as turn comes up. Terminate means when you finish it, you can close it, terminate. Okay, or kill. Okay. So if your operating system multi-threading is available, typically process start execution with the single thread. So initially you have only single thread in the process. This parent thread has the ability to create new threads. Different library procedures are available. So how do you create threads while executing? It used to manage threads. So these are some commands you use within a thread or process. How to create a thread? You use this command. Thread create command. Okay. What is thread create? When a new thread is created by another thread. So like processors, thread also can be created by another thread. Okay. When a new thread is created by another thread, usually the name of the procedure for the new thread to execute is passed as parameters. Okay. The thread, it is called thread identifier. That means the new thread. So you need thread identifier to identify the thread. That means the new thread is returned to the creating thread. So when you call this command, you have to pass parameter from this one to new thread, and new thread sending thread identifier to the parent thread. In some instances, the new thread might be created. In some instances, the new thread might be created as a child of the creating thread, giving rise to a parent-child relationship. In another instance, all threads might be created equally without a hierarchical relationship. If there's hierarchy, you have parent-child relationship. Otherwise, all are similar. Okay. So if you create thread, you have to exit also. So this thread exit. This library procedure is called when a thread has finished its work. So you terminate it. After this method, call is executed and the thread is no longer schedulable. Okay. Thread exit. The thread wait is the blocking situation. This procedure is used to block the calling thread while another is being executed. Then this one, thread yield, allows the thread to voluntarily give up the CPU. So if you are in the CPU, you can call this yield command to give up the CPU, so that you give space to another thread. You give chance to another thread. So voluntarily give up, that is thread yield. Since there are clock interrupts to enforce time sharing, so CPU time sharing done by a clock system clock interrupts. Right? Time sharing, this method called enable a thread to free the CPU and give the chance for another thread to execute. So if time slot finish, you can use this to enable another one to use that resource, the CPU. In addition to these methods, a wide range of other methods are available as well. So these are few commands. So there are some other commands or methods. Threads also introduce a number of complications to programming. So you can see, you have to think about these things and it complicate, make it more complex to program. As an example, if a child thread has the ability to create threads as the parent, then what will happen? If the parent comes blocked, thus the child threads has to be blocked as well. So while executing, if in case parent thread is blocked, do you have to block the child thread? So you have to make decisions. That's why it's making more complex. When a block parent thread becomes reactivated, thus the child threads become reactivated as well. So you have to decide those things. So these types of issues must be given due consideration when handling multi-threading program. So multi-threading program is bit complex. Okay. Furthermore, since all threads share the same address space, there might be some problems in memory allocation as well. So when you share the same locations, there can be some other issues if another thread delete something used by one thread, what to do and so on. Okay, so that's the introduction about threads. Explain the features of a thread model in your own words. That's here exercise for you to practice. Do you have any questions, so can we go to the next one? So if it is so complex, why we need to use threads? There are number of advantages could be derived by using threads. In many applications, multiple activities are carried out, right? By separating these activities into separate threads, it is possible to execute some of these threads in parallel. So it will make it faster. No? So that is one advantage. Then the second one, since resources are not attached to threads, like processors, you are attaching resources, but threads you are not attached. It takes less time to create new thread. So when you create a processor, it takes some time because you have to allocate memory, address space, and so on. But threads, you don't have to consider those things. So creating a new thread in an existing process is very faster than to create a new process. Okay, so that is another advantage. The time to terminate a thread also less than a process, right? You have to store less information. Therefore, you can quickly terminate. Similarly, switching between two threads in the same process is less time consuming than switching between processes. When you switch like CPU, you have to save certain things, load certain things. So threads are since very limited or lightweight process, it's easier than handling switching compared to process switching. Thread switching is easier and faster. Okay. Then another advantage is allows for performance enhancement for processors. If a process has different activities that are IO bound, right? So reading from a flash drive or something like that. And certain things are CPU bound. You need processing power. Sometimes you don't need not to have processing power if you are reading something from a file. You don't need the processor. You are not calculating anything. Right? So there are two things called IO bound, input output bound, and CPU bound activities. It is possible to create threads that allows activities to overlap and speed up the application. So same process, if you need to read something from a flash drive, pen drive, and also CPU operations, if you have different threads, they can run independent. You don't have to wait until one finishes, right? So it's a performance enhancement. Okay. Then enhance communication efficiency between executing programs. Since all threads in a single process share the same resources, like share global variables, the communication is faster. Unlike process, threads can communicate. Unlike processors, threads can communicate with each other without involving the kernel. You don't need system calls to communicate because you can use shared variables and so on. Then there are two types, user level and kernel level threads, two types of threads. Threads could be implemented in user level or in the kernel. Kernel means the system level, right? User level is the like programmer, right? Whoever use the computer. Kernel side is the like system file, system functions, and so on. So it is also possible to combine both methods. There are different advantages and disadvantages associated with each method. So it's the user level threads and kernel level threads. So if you see a diagram, it may be easier to understand. Now, so this is one process. These are the threads in a process. The circle is a process, right? So now whole space can be divided to user and the system, the kernel space. Kernel space and the user space. User space user can use. System space user can use. They are restricted. So user space you can have different now one process, since there are many threads, you should have thread table, right, to identify each thread. So this and the runtime system, you have thread table. Okay. So you can have similar other processors in user space. Okay. So since here you can see two processors, this is one process, this is another process. Kernel side, you keep the process table because system should know how many processors running and so on. But you don't need to keep here the thread table because threads are handled within a process. Okay, so let's see the other diagram also, then you will understand. This one. It's the kernel level thread. This earlier it's user level thread. So what will happen in the kernel level threads? You can see thread table also move to kernel because it's kernel level. You are handling different threads. So in addition to process table, so now two processors you can keep information about processors, but about each of these threads information you have to keep here instead of the user space. So this is the difference between kernel level threads. Okay, so user doesn't have to worry about these things. System is handling all those issues. So that's the difference between user level threads and kernel level threads. Now you have to compare advantages and disadvantages. So first the user level thread. Okay. The threads run on a runtime system, which is a collection of procedures that manage threads. Thread table is maintained by each process, each of the processes, to keep track of the threads belonging to that process. Okay. So thread table is managed by the process, not the kernel or the system. Okay. The user level threads. So maintained by each of the process to keep track of the threads belonging to that process. Each thread's program counter. So each thread they are a program counter, which one to execute next. Then stack pointer, history. Then they have registers and also state. What is the state? Running or blocked are stored in the thread table. Where is the thread table? It is in the process, not in the kernel, right? Thread table, you keep information about each thread. Okay. Whenever a thread is moved to the ready state or when it is get blocked, so transitions between states, a runtime procedure is called. This procedure checks to see if the thread needs to be blocked and if so, the information that is needed. Okay, sorry about the interruption. So threads, thread table, we have to maintain thread, right? Each thread's program counter, also what are the information in the thread. Thread table is managed by the runtime system. Okay, so runtime, it is changing while running the process. Whenever a thread is moved to the ready state or get blocked, the runtime procedure is called. This procedure checks to see if the thread needs to be blocked, and it's all the information that is needed to restart the thread. If you are blocking something, you need information when you want to restart. So you have to store them in the thread table. Okay. Next, it checks the table for a ready thread to run and reloads the machine registers with the new thread values. It is very similar to that different states, block one and running one, what you have to do. Okay. Therefore, the functionality of this is similar to the kernel's process table. So kernel keep the process table, process keep the thread table. So functionality is very similar. When a process blocked and change to running, same thing, right? Like a thread blocked and running again, similar operations but different information. So which is used to store information about process. So you can read the advantages and disadvantages. Try to read them. User level thread package. User level threads package can be implemented on an operating system that does not support threads. User level threads package can be implemented on an operating system that does not support threads. So let's say you have a operating system, earlier operating system, which is not supporting multi-threading. But program level user can implement the same concepts in your program. So user level threads package can be implemented on an operating system that does not support threads. But you have to handle all those complex things between threads. The thread switching is done using local procedures, for example, right? So you need to write local procedures in your program. This is more efficient than making kernel calls. No trap is needed. So you don't have to worry about the system calls within the program you are implementing. Context switching is not done and memory cache is not flushed, right? So you are not changing whatever loaded to memory and so on. Therefore, the scheduling in ULT means user level thread is very efficient, faster when implemented. Thread switching does not require kernel mode privileges. Program level you can do that. You don't need system level privileges. Since all thread management data structures are within the address space of a single process. So within single process you are doing all those things. No mode switching is needed for thread management. Each process can have a customized scheduling algorithm. Right? You don't have to worry about other processes. You can have custom scheduling algorithm, which could be designed depending on the nature of the application. So application to application, you can change the design. So what are the disadvantages? There are problems of how blocking system calls are implemented. So when there's block, how to implement? So we have to think about it. When blocking system calls are used, if one of the threads become blocked, it might have an effect on the remaining threads as well. To restrict this problem, non-blocking system calls would be used. As another solution, Def wrapper could be added around system call to check if it's safe to do the call. So these things you need to read leisure. I know maybe be difficult to understand unless you are familiar. So you have to read again and again. And if there are problems, you can ask. Okay. So therefore, probably I will stop here and leave you to read them, advantages and disadvantages. Probably next lecture we can read them again, right? If you don't understand anything, you can ask. Okay. So I'm going to stop the lecture here and leave you to read the lecture notes and go through. And if you need more information, you can refer the books or search from internet where you can download these things. Okay, so we'll stop lecture for today. Okay, thank you. Right, we'll stop the lecture there.